Likewise, if let's say you have a glass like this, right? And you just throw it into the air, you give it some, potential energy, it lands on the table, and then it's the original cup again. We just don't see that, right? And so there are processes that that we can imagine, but that conserve energy. There's nothing wrong with that, right? I could take this from the ground, right, and then throw it into the air, give it some kinetic energy that turns into potential, lands on top of the table, but we just never see that. And so this falls underneath the conservation of energy. And so the second law is, describes a lot of processes that don't happen. Another one that never happens is that heat, can flow spontaneously from a hot object to a cold object. It will not flow spontaneously from cold to hot. So in other words, if you have, two objects, one that's colder, one that's hotter, let's say this is the hot object. Let's say this is the colder object. What's never going to happen is this object get even hotter and then this get even colder, right? Because these molecules in here are bouncing around, bouncing around, bouncing around. It's going to smash into these, and then these are going to start to move faster, right? So you're never going to have the reverse. And so that's an important part of the second law as well. So this is the Kevin Planck statement. No process is possible whose sole result is the complete conversion of heat from a hot reservoir into mechanical work. So you're never going to ever have a 100% efficient engine, and we'll talk about why that is. And then no process is possible where the sole result is the transfer of heat from a cooler object to a hotter object. That's the Clausius statement. So both of these fall under the second law. If we look at that piston from the original picture that we had, and we consider that, right? We have that hot gas inside here that's expanding and pushing that piston over, right? And as it pushes that piston over, that gas is going to naturally cool down. And so, as that happens, the gas is expanding, and these molecules are going all over the place. They're not necessarily all lined up, right? So they're all going all over the place. And therefore, there's some kind of chaos in there, but, we're harnessing some of that, right? Now, if we were able to get all those molecules to line up, let's say we got all those molecules to line up and we're pushing this piston over perfectly, right? And those molecules are perfectly pushing the piston over. And as they do that, they're exerting all their energy, and all those molecules, you exert all their energy. If they do that, then what would actually happen is, if it could do that, the final temperature would be 0 Kelvin because it exerted all of their energy, right? And we know that's impossible. Really what's happening is it's pretty disordered. All these molecules are going all over the place. Some of them are pushing that piston over, but some are smashing into the wall here, to the wall here, the wall here, and to each other. So it's more chaotic. And so that's where you're never going to have a 100% efficient engine where all those molecules are lining up. So a good example of an engine where we can evaluate this is where we have water, we have a boiler, and we're heating this water up, it's turning into steam. That steam comes through here. It's pushing a piston over. It's like that made of lock, simulation I showed you guys on that first day, pushing the piston back and forth, back and forth, back and forth. And or it could be like a pinwheel here. The hot steam comes in, pushes this around, cools down, and then goes to the condenser, turns back into water, and then we can take that back up, and that boiler can heat it up again. We have that process continuing. And so, we're never going to have a 100% efficiency with that. You wouldn't want to put your hand here right after that, piston's pushed over. It's still going to be pretty warm because it didn't exert all of its energy. It didn't use it all to do practical work. All right, so this steam engine receives 4,400 joules of heat per cycle, does 1,600 joules of work. What is the efficiency of this engine? So if you want to even just try to figure this out, logically here, see if you can figure out the efficiency of this engine without me giving you any kind of equation or anything. See if you can think through that. Go ahead and pause the clip and try this, and then when you're ready to check, you can hit play to continue. All right, so efficiency is, work over heat in. So, 1,600 joules of work, heat in coming in 4,400 joules, so only 36.36%. And so that would actually be pretty decent for a steam engine if it got that much out of it. Steam engines are pretty inefficient. So, we're going to be talking about repeating cycles with engines coming to the initial state. The heat coming in, QH, is what we're dealing with there, how much work, W, and then the rest is exhausted, QW there, and the low temperature reservoir. High temperature reservoir is where we're dealing with Q down. And so when we're dealing with engine efficiency, we're dealing with, how much work are you getting based on how much QH is coming in. And so you could even just think through this logically like we just did there. Now, if we consider an engine, right, how much work is being done, we can look at QH. That's the the heat coming into the engine, and then we subtract QL. That's the exhaust, and then we can figure out how much work we get. So if we replace this, right, we replace W with QH minus L, we've got that. And so this is another way that we can calculate it, 1 minus QL over QH. And the less this is, right, the smaller the QL is, the less that's lost, the higher the efficiency will be. And then if the none is lost, right, then this is 0, you'd have a 100% efficient engine. And so if we have a car engine that's performing 2,200 joules of work, we'll say, and it's exhausting 6,700 joules of heat, we want to find the engine efficiency, we can do that. And yeah, so go ahead and pause the clip, give this a try, and then when you're ready to check, you can hit play to continue. All right, so in this case here, QH minus QL. QH coming into the engine would be 8,900. QL that's lost is 6,700. So this would be 24.7% efficient cycle. Now, Carnot investigated how to convert heat into useful mechanical work. And, we know that we can't have a 100% efficient engine. But is there actually a limit to how efficient an engine can be? And so that's what we can evaluate now. We talk about the Carnot engine as essentially the ideal engine, the heat being transferred in an ideal situation, and it's reversible, and we're assuming no friction. So in this cycle, and this is the most, this would be the perfect cycle: isothermal expansion followed by an adiabatic expansion, isothermal compression, adiabatic compression. And let's take a look at an example of that here. So if we have isothermal expansion, then adiabatic expansion, isothermal compression, adiabatic compression, this would be the heat in here. This would be the heat going out, QH, QL, and then the practical work that's being done would be that area inside there. And so it'll be important that you can draw that. You can draw out the ideal Carnot engine, and assuming no friction loss, and 100% efficiency there with it. So for an ideal reversible engine, we can write this in terms of temperature, where we have TL as the exhaust temperature, the low temperature, and then the high temperature is QH. And we must have this in Kelvin. Because if you think about it, if you had this in Celsius, that could screw everything up, because if, let's say, QL is 0 Kelvin, right, then you'd have a 100% efficient engine. 0 degrees Celsius, though, that's more, manageable. Then you could say, oh, I have a 100% efficient engine, right? But that's really not true. So again, we can only have 100% efficiency if our cold reservoir ends up coming to be absolute 0. And real engines have some frictional loss. The best can achieve 60 to 80% of the Carnot efficiency. So here in M10, if an engine is 38% efficient, what's the exhaust temperature if the temperature of combustion is 623 Kelvin? So let's consider that here. We have our combustion is 623, 38% efficient. Yeah, why don't you go ahead and try this one. Go ahead and pause the clip and see if you can determine the exhaust temperature if we have these values here. All right. So you should have gotten, being careful with the algebra, cross multiplying, then dividing 386.26 as TL. So we start with an exhaust temperature or a engine temperature 623. That's TH, and then the exhaust is 386. That's TL. The greater these values are different, the more efficient it is, right? Because the smaller this TL is, the more efficient the engine is. In this case, it was only 38% efficient. So the definition of a change in entropy, when a certain amount of heat added, is delta S equals Q over T. And so, the total entropy of an isolated system never decreases, and so it always increases with an isolated system. And so let's take a look at some situations here. All right, well, let's go ahead and define these, right? So the change in entropy is a joule per Kelvin, right? So, and then Q is heat going into the system, and then T is Kelvin temperature, average temperature for the process, and the key here is average temperature. The heat going into the system, let's say you're cooling the system, then you'd have negative Q in there. And if the change in entropy is positive, then randomness or disorder has increased, right? So, if you have liquid water and you're heating it up and it's turning into gas, it's going to be disordered, right? Spontaneous changes involve an increase in entropy, right? So natural processes is going to more disorder. And entropy can only go down when energy is put into the system. And so, if you're decreasing entropy in one area, you're increasing in the other. And the overall process, if you consider the whole thing, it's an increase in entropy. All right, so this is M13. What is the change in entropy of 0.29 kilograms of water at 5 degrees when heated to 100 degrees? And then part B, how much more entropy change for the continued warming until all the water becomes steam? So if you want to pause the clip, and this, it's going from 5 degrees to 100 degrees. Again, you're going to need to have temperature in Kelvin. You can do the first part with MC delta T, and then let's actually, I want you to see if you can go through the whole thing, and then when ready to check, you can hit play to continue. So go ahead and pause the clip and give this a shot, and then you can check in a second. Okay, so we should get for the heat going in. What's going from 5 degrees to 100 degrees, 4186 is the specific heat, so that's Q going in. And then when we look at the entropy change, we know how much heat went in. The average temperature, right, is 100 plus 5 over 2. That's the average temperature. We add that to 273, and that will give us the average temperature Kelvin. So the overall entropy increase would be 345. 0.4 or 0.299 joules per Kelvin. How much more entropy change if we continue to bring this all the way to steam, right? So the latent heat of fusion we've got here. So this is the amount of heat that it would take to make it actually change into water, water to become steam. And we know that that temperature is going to stay at 373. It's 100 degrees plus 273, then we have that there. So, 1754 for a total of 2108 joules per Kelvin.